Okay, welcome back. So in the last video, we were just kind of talking about the history of t-tests and this kind of certain example here where we don't want to use all of our population to experiment on. We just want to use a small sample and then see if we can make inference about the whole population based on this small sample. In this case, whether or not the fertilizer increases hop yield. Okay. So we'll just kind of get into a little bit of some nitty gritty details, just a bit. Again, this class is very much not a math class. This is an applied stats class. So I don't so much care that you understand the calculus that goes behind all of this. I do care that you have at least a tiny grasp on it. And it doesn't have to be now, it could be later or whatever. But just being familiar with these kind of ideas is always good. Okay. So old Billy Gossett here, developed the T distribution. And historically, before this distribution was used, we used what's called the normal distribution, which is that kind of symmetric and bell-shaped bell curve, the normal distribution. We used the normal distribution to make inference about things. So just kind of taking a step back here, if you recall from intro stats, when we were doing this kind of stuff, if you took it with me, and if you didn't take it with me, you probably did this as well. But when you're doing t-tests by hand, what you have to do is calculate two things, along with many other things, but specific to t-tests is that you needed to calculate a test statistic and also a critical value. And if you recall, both of those things would fall somewhere along the distribution here. And if our test statistic was either very far in front of or very far behind our critical value, then we were able to say that there was some sort of effect, right? Okay, but that's for big samples. That's for things that follow that kind of normal distribution. It turns out, though, that when you have these smaller samples, that's not necessarily the case. So the T distribution is actually able to account for the fact that we have small samples. Okay? We know that small samples are going to have a slightly different distribution as far as theoreticalness goes. It's going to have a slightly different looking distribution, and I'll show you that here in a moment. The nice thing, though, about the T distribution is that it's ever changing. Okay, so it's 100% based on the size of the sample that you have. And I'll show you here in just a moment. But as the sample size increases, the T distribution becomes more like a normal distribution. And that makes math, if you were doing it by hand, very easy. Of course, we are not doing anything by hand. We're doing everything via computer. So I have this sort of thing X out here. This is your traditional T table. If you took intro stats from me, we've never even touched this. We used a calculator instead. But if you took it from someone else, you might remember this and be kind of annoyed at looking at this. We are not doing this, though. Thank the Lord. We're able to get way, way more accurate results that the T-table can't really give us. Okay, so we're talking about T distribution, how it changes. Let's take a look on how it actually changes. So I've got some code here. This is not necessary. You do not have to know what's going on here. You do not have to know how to do this or whatever. I'm just showing you just in case you wanted to know. This also, you don't need to read in any data. So this just works as is. Okay, so traditionally, when you're doing this by hand, let's just look at this normal curve, this red line here. What you would do is you would say, okay, I have my data and I'm going to summarize it based on this test statistic. I'm going to put it right here or whatever it equals. It could be right here. It could be right up here. And then I have a critical value that I'm supposed to exceed if I want to make any, conclusions about our test, whatever we're testing, okay? And the further away our test statistic is from our critical value, then the more there was a more of an effect as far as the experiment goes, okay? But that's on the normal curve. We can see here that the T distribution is not quite as high. It does not grow as tall, but it makes up for the fact in that its tails are a little bit fatter. at least compared to the normal distribution. And then this is with a degree of freedom of 1. So 1 degree of freedom, essentially that is a sample size of 2. Okay, we'll get more into what degrees of freedom actually are. As far as I'm concerned, when you're in practice, it does not really matter so much, at least with the types of tools that we're going to be using now. As you get into more complicated analysis, degrees of freedom do come into play, kind of tells you the overall complexity of the thing that you're using. But for now, we'll just know that this is essentially an analog for the sample size. Okay, so the smaller the degree of freedom is, the smaller your sample size is. And we can kind of see that here. Okay, so this is our theoretical distribution compared to a theoretical normal distribution. But as that sample size grows, so this is a sample size of 6 now with n minus 1 degrees of freedom. Math, don't worry about it. But we can kind of see here that these two things start to become very close to each other, very similar as far as shape and spread go. Still a little bit, the t distribution is not as tall, and it still has these kind of fatter tails. But as we keep going on, we can kind of see how that changes. So the bigger the sample we have, the closer to normality we have. And that's kind of the big thing here, is that the bigger your sample size is, the better, essentially. Now, there are some lies that were told to you in intro stats and maybe some other stat classes that 30 is a proper sample size. Not necessarily true. And I think I even told you that in intro stats. That's just to make things easy, make things sort of easier to work with by hand. You don't have to take as much into account because of this idea here. Okay, so as the sample size grows, the t distribution becomes more like a normal distribution. And this is all because we are estimating the variability of the population based on the variability of our sample. Okay, and again, we're going to get more into practice here. So if this is all going over your head, please do not fret, because this is an applied class, and the math, in my mind, at least, is not as important as the conclusions we'll make here in just a little bit. Okay, and the last one. So you can set the degrees of freedom or the sample size to effectively infinity. And we see here that those two lines are perfectly overlapped, which makes things very nice. Very cool. Okay. Now, here is a big deal. And let me take a quick sip of coffee here, just so I don't blow out my throat. Oh yeah, I feel rejuvenated already. Okay, so we are getting into the world of language here as far as English and statistics go, okay? So when we say something is significant, what do we mean? Okay, well, in English, I've got kind of the definition here. Let me move that up. Got the definition there. In English, effectively, we mean something that is notable, something that is important, kind of, right? However, in statistics, that is not true. When we say something is statistically significant, what we actually mean is that the result that we saw is unlikely due to chance, okay? So it is not due to just randomness in the world, that there is some mechanic kind of behind the whole thing. So you can have a statistically significant result that is not practically significant, okay? The math is the math. The math is going to do whatever it's going to do. But whether we decide that it's practically significant, or at least in English terms significant, that's on us, okay? So these two ideas are totally different. Okay, now how do we quantify this statistical significance? How do we determine whether or not this was due to chance? Well, here we are, everyone's favorite, p-value. That's how we calculate the overall statistical significance of whatever conclusion we saw, or whatever result we saw, and whether or not we can trust the conclusions we're about to make, okay? And so a p-value is just the probability that your results from your sample, okay? So the thing that you're testing in your small sample occurred by chance or just due to total randomness. Okay, total randomness. Now, a lot of people put a big emphasis on probability as far as, flipping coins and marbles in a bag and whatever else. We're going to skip over that kind of stuff because that kind of probability is not necessarily the same as this kind of probability that we're taking. And so we'll see some more sort of examples here in just a moment. But do know that, this idea of probability, understanding the basic idea of it is good. But again, it's not totally necessary for right now that you know how to calculate the probability of drawing one marble that's red in a bag of 49 other blue marbles or something like that, right? Two totally kind of different ideas here, related, but not exactly identical. Okay, so long and short, we use p-values to determine whether or not the result we saw was due to chance, okay, due to randomness. Okay, so I'll fill that in again here. We have p-values, again, definition there. But also we have this idea of distance, okay? When we are looking at the difference between two samples, we can effectively determine, well, if those two samples, maybe if we were to plot the histograms, if those two histograms are really far away from each other, then that is probably true across the whole population, okay? Not just in our small sample. And the further they are away from each other, the more likely it is that that is true in the population. Okay, and how do we quantify that distance? Well, we have what's called a t-value, and that's just the distance that the tested difference is away from zero in standard error units. We'll get to this in just a little bit, but let's focus on this sort of chunk right here. So when we are doing t-tests, we have two different samples. One sample with our experiment and one sample that does not have our experiment. So sort of like a control group and an experimental group. Sometimes that's kind of the most classical example. Okay, and we are just testing the difference of the means of those two groups. Okay, and a difference in means of 0 means that there is no difference. Okay, so that essentially means that those two samples are right on top of each other. If we were to draw the two samples as a histogram, then we would not be able to really see so much any differences between the two. However, as that difference grows, the two histograms kind of start to separate, and then they go really, really far as that difference grows further away from 0. And so as that difference grows, that probability that that thing that's happening was due to chance goes down. So as that t-value increases, p-values tend to decrease, okay? And the same can be said in the other direction. As that difference decreases, as that difference comes closer to 0, the p-value increases, okay? So it's this kind of inverse sort of relationship between these two things. Now, these two things are 100% related. Okay, you can kind of think of this t-value as our test statistic that we calculated by hand in Stat 2050. Okay, except we're making it a little bit easier because the computer is doing the work for us. Okay, so this represents a distance, a difference between our two samples, and the p-value represents the probability that that distance that we saw, that difference we saw, is due to chance. Okay, and we'll just take a look here. So let's say our red curve here is our control group, and let's say our blue curve is the distribution of our experimental group. Okay, and right now, there's quite a bit of overlap between the two. In this case, the what are we saying? The fertilizer is increasing yield by just a bit, but not enough for us to conclude that it's at least going to be big enough to see in the whole population, okay? And that's kind of denoted by this gray area, in that these two distributions have this kind of shared area, and that's our p-value, okay? And then the peaks here, in this case, we'll just say represents the mean. We see that that difference there is going to be really small, okay? But let's say that we then maybe tried a different type of fertilizer. Our red curve represents the control group. Our blue curve represents the experimental group. Now we see a bigger difference between crop yield, okay? That t-value is reflected as that difference, and the p-value, that shared area beneath the two curves, beneath these two histograms, or density curves in this case, is represented here, right? That p-value is the probability that this is just due to chance. And we move on, maybe to a different type, and we see that as these two samples grow even more different, that t-value grows and grows and grows, and that p-value becomes really, really small. So we can say that it is very likely, since this p-value is so small, and possibly that this t-value is so large, but mostly that this p-value is so small, that this difference likely is true across the whole population because it's so small. We have got a lot of evidence, a ton of evidence, that this relationship is true when you blow it up to every hop in your field, not just the ones in your sample. And of course, as these grow even further and further and further, the more different they become, the further apart they are, the more evidence we have to say that, you know, the fertilizer works in this case, as far as increasing crop yield. Okay, now this is not exactly what's happening in the background as far as what the computer is doing, but this is, I think, the best way to kind of visualize how p-values and t-values and our two samples kind of operate, okay? Again, this is not always true. It's not always as clean as this, but I will show you a couple examples here in just a moment. So with that, we have the last sort of topic as far as this intro stuff goes, introductory material. I'm going to stop the video because I've been talking for a bit, and we'll pick it up right here in just a moment.